Hello everybody. In this video we will talk about measurements and data processing. It is chapter 11 of your book, and we will discuss the uncertainties, certainties, random errors, systematic errors, how to read uncertainties, how to propagate those uncertainties. This is your syllabus, all the points here. Let's talk about some basic stuff. Whenever we collect any measurements, you all did your IA as well. Whenever we collect any measurement or we do any lab, we have a quantitative data and a qualitative data. So I don't think I have to get much into detail here. The difference of the qualitative data like fizzing, flaming, or melting, or the quantitative data that we talk about numerical data. Whenever we calculate the quantitative data, one thing that comes up is called uncertainties. When taking a data from the measurements of a physical quantity such as a temperature, mass, or volume, whatever that is, there is a possibility that the measurement that you're taking is true or not true. This is because we can never determine the exact value of a physical quantity. Every piece of quantitative data has an uncertainty, okay, and we will, because of some random errors or systematic errors. So that's why, earlier you probably have seen that we talk about estimated digit. So there is never ever, whenever we take any measurements, is always true or final or accurate. It has some degree of estimation involved in it. So anyway, let's keep going. We will also talk about precision and accuracy. Precision is how close the set of data is within how close the numbers are or the measurements are within a set, and accuracy means how close the data is to the true value. I'm sure you all know the percent error. You want to see how far you are from the accuracy, and for that we calculate the percent error. So measured value minus a known value divided by the known value times 100. It's an absolute value, so the answer is negative, never negative. Calculating the percentage error can be used to determine the accuracy of the experimental work. Precision means how close the data from a different measurements is to each other. For example, a set of readings, you have 34.2, 0.3, 0.5. They're pretty close to each other, so this data would be quite precise. Okay. A great degree of precision can be achieved if we use a measuring instrument which allows us measuring raw data to a greater number of significant figures. Okay, so instead of having a beaker that just tells you this is 50 milliliters, I need a graduated cylinder that can tell me 10.1 milliliter. But even that, I can have a one that can tell me 10.01 or 10.001. So you see that the maximum number of significant digits that I can get, the precise the data will be, rather than having a whole number or having one decimal space. So the bigger the significant figures are, the better the precision is. So a balance which allows us to record the mass to 34.215 gram or 34.265 grams, it produces a range of values. It has a greater precision. Okay, so however, you need to be aware of the following, that if in this case the uncertainty is 0.01, you have the data of 65.14, is more precise than 65.1, as I was telling you before. It could be less accurate if the true value is 64.9. The true value is to the 10th place. So examples of great precision but little accuracy. If the top of the meniscus is red, you can have great precision but less accuracy because you're using an inaccurate method. So of course you will have the less accurate data. So let's talk about whenever we do these experiments, what kind of errors do we deal with? We have random errors, random uncertainties. These are the uncertainties or the errors caused by the limitation of the measuring instrument. That you are not recording the value correctly. and it results in the readings that are either above or below the true value, okay, exact value. The amount with which the value is above or below indicated as an uncertainty range. So, and we show the range by plus minus. So it is plus, above the true value, or it's below the true value. So let's say the true value is 5.2. Uncertainty is going to be the smallest digit for the digital equipment. So it is 0.1. That means for this measurement, the accurate value could be, it can range from 5.1 to 5.3. Okay, so that is the range of your measurement. This means that we are not completely certain that if it is 5.2, okay, we are not certain that the last digit is accurate. Okay, it could be between 5.1 or 5.3. There's uncertainty range is 0.1 for this and 0.1 for this, so it will be 0.2. So random uncertainties is the uncertainty that is caused by wrong measurement, okay, wrong reading. If we do not indicate the uncertainty clearly, then it is assumed that the last digit is the uncertain digit, and that the accurate value is between 1 unit above and 1 unit below whatever the last digit is. So if your last digit is 4, so 3.454 and 3.452, then the uncertainty range is, between these two, it's like 0.002. If we are given uncertainty, it's easier to calculate it. If we're not given, we just assume it like this. Well, random uncertainties affect the precision of the numerical data. The narrower the range is, the more precise the data could be. If it has a long range data, there is a more possibility of uncertainties. It can be above or below the exact value. Random uncertainties are indicated by the last digit in the numerical value, as this digit is usually uncertain. As I was telling you, the last digit is always the estimated digit. So whatever your last digit is, that is your uncertain digit. Random uncertainties cannot be eliminated, but they can be reduced. How? By taking repeated trials and then averaging those values. Then average value could be closer to your true value, okay, and using the most appropriate measuring tool. So this is how we can reduce the random uncertainties or random errors. Determine the uncertainties by using different equipment. So if we are using the analog equipment, okay, we will use half of the last digit as our random uncertainty. Okay, we are using a digital equipment, which is usually the case. The uncertainty will be the last scale. The smallest scale division will be your uncertainty. So in this case, it will be 0.001. So whatever your, if it is 5.2, then plus minus 0.1 is your uncertainty. So if for digital scale, you just take the last digit. So if the equipment is incremented by 0.1, then your uncertainty is plus minus 0.1. If your equipment is analog, then you take half of that. So it will be 0.05 for this in this case. But anyway, random uncertainties, one more time, are due to the limitation in how you record the measurement. Like if you are reading the upper meniscus instead of reading the lower meniscus, that could cause uncertainty. We always count the last digit as the uncertain digit, so it will be plus or minus of the last digit. If we are not given a proper digit, then we take the range of the last digits, okay. These uncertainties can be narrowed down. They cannot be eliminated, but they can be narrowed down by doing multiple trials and using a more precise equipment. So uncertainties of commonly used instruments. Usually when you are doing an electronic scale, the uncertainty is going to be plus minus 0.01, because usually the scale is reading to the 100th decimal space. Your burette, usually it's written on the burette that the uncertainty is 0.05 cubic centimeter. Thermometer is 0.1. So these are the common uncertainties the stopwatch is going to be 0.05. So let's talk about systematic uncertainties or systematic errors. This is the error that is part of your procedure. Okay, it is something you cannot fix by doing repeated trials. Because if your procedure is wrong, no matter how many times you repeat it, you will get a wrong data, or some kind of a error in your measurements. So systematic uncertainties are different than the random uncertainties. So this is caused by the imperfection or limitation in the equipment that you're using. For example, your weighing scale is not calibrated properly, or the solutions that you're using, they have been sitting for a long period of time. So solutions have lost their activity. They are not very active reagents. Your procedure, as I said, is wrong, or no insulation in your calorimeter or in your uh, cup that you're using, heat loss to the system that you cannot control. You cannot cover your material, so there is a heat gain or loss to the surrounding. Uh, so these are all part of your systematic error that you just cannot avoid no matter how many times you repeat it. Let's say you're doing a dehydration lab and you want to heat the um, the hydrated compound. This is something you can cover by repeating it over and over. But if something is wrong with your sample, then there is nothing you can do about it. So these are the systematic errors. They affect the accuracy, of course. Such an error always occurs in the same direction because you're always repeating the same mistake. It either makes the data higher or lower than the true value. So the examples of systematic errors, because sometimes these are the questions on the IB exam, that they give you a scenario and they ask you, is it a systematic error or is this the random error? And if once you choose which of the two it is, then what are your suggestions to fix that error? So you need to see that either it is systematic or random. So here are the examples for the systematic error. A balance incorrectly calibrated, so it's always read the mass higher or lower. Um, Consistently reading the burette, like top of the meniscus instead of the, the lower meniscus. You're always reading the top meniscus. So then no matter you take one trial or 30 trials, if you always read the top meniscus, you're always going to get a wrong data. Using impure chemicals, chemicals which are not completely anhydrous, means they have absorbed some water, and for the chemicals who are required to be anhydrous. It's measuring a dry mass when the chemical has not dried out yet. Difficult to observe a distinct color change during a titration. It's the nature of the experiment that it is hard to tell. Poor insulation in the enthalpy experiments. Uh, Reaction time when measuring the time intervals, and using the assumed values. So these are all the examples of the systematic errors. They can be reduced by improving the procedure, equipment, or material, but not by the repeated trials. Because if your equipment is not calibrated properly, no matter how many times you repeat, you will not get the right data. So this is very important topic in reference to your exam. You must understand the difference between a random error and what are the examples of the random error and how can you eliminate it, and systematic error and what are the examples of the systematic error and how can you eliminate it. The next topic, as we have talked earlier, precision and accuracy. Precision is how close the set is within the data, and accuracy means how close it is to the true value. To calculate how accurate your data is, we use the percent error. So I don't think we need to go over this too much. Let's keep going. How the two, the accuracy and precision, or the random or systematic errors, they can impact your measurements. Your measurements could be by having random or systematic errors. There is a possibility your data is neither accurate nor precise. There is a possibility it is precise but not accurate, and it is a possibility it is a precise and accurate, the way you exactly want it. In the evaluation, a large random and systematic error means that you have a poor technique or procedure using less precise measuring instruments. So you're having both kind of, for neither accurate nor precision. That means this is the mistake that you made. So if this is the outcome of your experiment, that you, let's say you calculated the density and the density is neither accurate nor precise, that means you have a large random and systematic error. You used not only a poor technique, but your equipment was not proper either. If your data is precise but it is not accurate, that means that you have small random errors but large systematic errors. So accuracy is directly linked with systematic error. If your data is both precise and accurate, then small random error and very low systematic error. So this is also very important from your exam perspective. They can give you a scenario. They can say, okay, this is the data. Which one do you think which error it is? Or if this is the data, which one you think is, who is responsible? Is it random error or the systematic error? Well, the next topic is significant figures. We have learned significant figures. We know how many, all digits except 0 are significant. How do we add or subtract, significant digits? When you add or subtract, we go by the decimal spaces, least amount of decimal spaces. When you multiply or divide, we go by the least number of significant digits. So let's go back to the uncertainty calculations. If we have uncertainty, how do we calculate it with our data? So there are two kinds of uncertainties. We can have absolute uncertainties, or we can have relative or percentage uncertainties. To calculate a percentage uncertainty, we will take the absolute uncertainty, divide by the measured value, multiplied by 100. We will do a lot of examples to figure this out. How do we report a percentage uncertainty? So the common way is that it was always reported by one significant figure. So we calculate the percentage uncertainty, but we convert it back into absolute uncertainty before we report it. I will explain that with examples. So let's first of all talk about uncertainties here. For addition or subtraction, we use absolute uncertainties. So for addition, let's say I have a 4.35 hertz, the frequency, and I have 2.12. Here is the absolute uncertainty for 0.02, plus minus 0.02, and 0.01 is the uncertainty for this. When I add these two numbers, I will add the uncertainties. So 0.02 plus 0.01, I will add my uncertainties. So when I add these numbers, this is my total hertz frequency, and this is the uncertainty. So the rule is that when we are adding or subtracting the uncertain values, we will add absolute uncertainties. When we are multiplying or dividing, okay, we convert the absolute uncertainties into percentage uncertainties, and then we convert the percentage uncertainties back, after adding them, back into absolute uncertainties. So here we go, calculating using measurements. So we are dividing this number, meters, divided by the seconds. So meter per second. Here is the uncertainty for the meters. Here is the uncertainty for the seconds. All right, so to calculate the percentage uncertainties, I have to calculate it for each value. So I'm going to do it for the meters, for the distance first. So for the distance, I will take my absolute uncertainty, divide by the value. You remember the formula here. We take the absolute uncertainty, divide by the value, multiply by 100. So I will take my absolute uncertainty, divide by the value and multiply by 100. Same thing I do for the time, 0.01 divided by 2.1, I multiplied by 100. So I have my percentage uncertainties. These are the percentage uncertainties. I will add the two percentage uncertainties. Okay, this is the addition of the two percentage uncertainties. So this was the answer of my meter per second. Okay, this was my calculation. And for 21 meter per second, my uncertainty is going to be 2.5%. Now, before I report this, I need to convert this percentage uncertainty back into the absolute uncertainty. So I will calculate 2.5% of 21. So 2.5 divided by 100 multiplied by 21, that is 0.5. That means my uncertainty is right here. 44.01 meters divided by seconds. These are the absolute uncertainties. But after doing all this math, after going through this whole procedure, with 21 meter per second, my uncertainty is going to be 0.5 because I converted my 2.5% back into absolute uncertainty, which was 0.5. This is how I will say plus minus 0.5 because I always have to report it by one significant figure, by one significant digit. So rules are that to convert the absolute uncertainty into a relative uncertainty. Once again, how? I will take my uncertainty, divide by the value, multiplied by 100, take my uncertainty, divide by the value, multiplied by 100, and then I add them together. Okay, so convert the absolute uncertainties into relative uncertainties, then add the relative uncertainties, and then convert this back into the absolute uncertainty. So this is how we will calculate our uncertainties when we are adding or subtracting or when you are multiplying. So these rules will be part of your examination that you need to practice and get better at. Let's see if we have more examples of this. So when you're multiplying or dividing by a pure number, so I'm multiplying this number with this number. So I have this uncertainty here, 0.1. Okay, my uncertainty, I will add them together, 11.0 plus minus, when calculating the averages, we're calculating the averages. Okay, so when calculating, multiply or divide the absolute uncertainties by a pure number. So calculating unknown uncertainties, unknown concentration from a titration. So let's say we're doing a titration. We have a volume of the hydrochloric acid. This is your volume measured in the burette. This is the uncertainty I told you before. The burette is plus minus 0.05. The concentration is moles per cubic decimeter. The volume of the base is this. So when I calculating the concentration of the base, I'm doing the volume multiplied by the concentration divided by the base. So this is what I'm doing with the uncertainties. Propagate the uncertainties. So I have to calculate first. So this is the uncertainty of the volume. So you see here 0.05 divided by 24.5 times 100. Okay, that is the uncertainty of this. Then I have 0.03 divided by 5 multiplied by 100 for the division. So I add the 2% uncertainties. And the step 2 is I add the 2% uncertainties, and then I convert the percentage uncertainties back into the absolute uncertainty. Okay, so presentation, this is my absolute uncertainty. So this is calculating density. We have mass divided by the volume. So this is the mass, this is the volume, this is the uncertainty of the mass, this is the uncertainty of the volume. I have to calculate them separately. So 0.1 divided by 44 times 100, 0.2 divided by 21, 2.1 times 100. So these are the 2% uncertainties. I will add the 2% uncertainties. So when I add them together, I get this. This is my 2% uncertainties, and then I will convert it back into the absolute uncertainty. So this is about it. That's all you need to know for for measurements and uncertainty unit. So if you have any questions, let me know, but that's all we wanted to talk about in measurements and data processing. How do we collect the data? How do we how do we measure uncertainties? How do we add or subtract them? So thanks a lot, everybody.